All right, so this is section 5.1 of Math 146. We're going to be talking about some applications involving right triangles. This will actually be a really short video overall. Um, it really should be kind of a repeat of stuff that you've already seen, but if not, hopefully this won't seem too difficult. Some of the basic things that we're going to need is we're going to need Pythagorean theorem, which of course is, oops, let me use a different color, is a squared plus b squared equals c squared, where c is the length of the hypotenuse, a and b are lengths of sides of a right triangle. And we're going to need to know our trig SOHCAHTOA identities, which we'll get into as we go. So the general idea is you have to be given a little bit of information, obviously, about your right triangle in order to solve it. So we'll start off really basic. We're going to start off with just actually solving um, specific parts of a right triangle. So let's say that we are given this right triangle. Of course, we know that that lower right-hand corner angle is 90 degrees. We're going to be given that this side over here is 2. We're going to call this angle on the inside B. We're going to call the side over here A, and we're going to call the hypotenuse C. And we're going to be told that the angle up at the top there is 40. Now, if this was a special right triangle, a 30-60-90 or a 45-45-90, all we would have to know is one side in order to solve the other sides. In this case, it's not one of those. So we're going to have to use trig in order to figure this out. And if we already knew two of the sides of the right triangle, then we could use that to figure out the third side by using Pythagorean theorem. In this case, I only know one angle other than the right angle, and I know one of the sides. So we're going to have to use some trig to figure out most of the rest of this. Now, the one thing that we should know right away is we should know angle B. And that's because all the angles within a right triangle, within any triangle, have to add up to 180 degrees. And since I already have a 90-degree angle and a 40-degree angle, that would add up to 130. Well, that means that B has to then be 50 because that's what's left over. So we've got that B equals 50. The only other two pieces remaining are little a and c here. So we're going to have to use trig in order to figure those out. Now, the fact that I already know B is good because I could use multiple different trig values here in order to do this, trig identities. I'm going to go with the 40-degree angle just because of the fact that was the one that was given to us. If we wanted to find A, well, what we know is that the angle in question is 40, and I know that the side 2 is the adjacent side. So I'm looking for the opposite side of 40. I'm given the adjacent side, so we should use tangent in order to find A. And tangent of 40 degrees would equal opposite A over adjacent 2. So if I want to solve that for A, I'm going to multiply both sides by 2. And that would be your A value, whatever that is. Now, notice this is in degrees, so if you do this in the calculator because it wants a decimal approximation of some kind, you're going to have to make sure your calculator is in degree mode. Now, that would give us A, and I think that works out. I've actually worked out, hold on, where did I put it? There it is. A works out to be approximately approximately equal to 1.68 if we go two decimal places. Um, could I still use that to find C, the fact that I now know A, and I could use Pythagorean theorem? Yes, you could. It will be a pretty decent approximation for C, but it's not going to actually give you a better approximation than it would if you use trig. And you could always try this out. I'm not going to go through it, but you could try it out and see how much of a difference it's going to be off. Instead, to find C, I'm going to go back to the fact that I already know that angle A, I should say, is 40 degrees. So that would be the hypotenuse I'm looking for in C, and I've already got the adjacent too. So adjacent and hypotenuse is going to be cosine. So we're going to say that cosine of 40 degrees is the adjacent 2 over the hypotenuse C. Now to solve for C, we're actually going to have to multiply both sides by c. It's going to look a little weird having that c out in front of the cosine. And then we'll have to divide both sides by cosine of 40. So we get that c is equivalent to 2 divided by cosine of 40 degrees. And again, in the calculator, that's going to give you an approximate value of 2.61. And what you would see is if you use the 1.68 to be A and the already known side of 2 and use Pythagorean theorem, it's going to give you a C value which is slightly different than what we have there. And that's because we rounded A. So that's why it would be a little bit different. If you don't round A and go out, you know, a bunch of decimal places, then your difference is probably not going to be very much. But anyway, that's pretty much what it means to solve a right triangle. You're looking for whatever the missing pieces are. All right, so let's do one more of those, and then we'll get into an application other than just a standard triangle. So let's say that we are given, again, a right triangle. This time we are given that one side is 2 and the other side is 3. We are missing the hypotenuse C, and we don't know either angle A or B. Well, in this case, now we're given 2 of the sides. It makes sense to use the Pythagorean theorem, excuse me, to find the missing side because we can get an exact value. So to find C, we're going to do 2 squared plus 3 squared equals C squared. 2 squared is 4, 3 squared is 9, so adding those together, you're going to get 13 equals C squared. Taking the square root of both sides, we get the square root of 13. No need for the positive or negative here because we are talking about the length of a side, so it has to be positive. And if you wanted the decimal approximation, because maybe that's what the computer wants you to put in for your answer, it would be about 3.61. I personally prefer to leave it as the square root of 13 because it is exact. Now I can use, basically I can use any of these 2 sides that are known, but since we approximated C as a decimal, or you could use the square root of 13, it doesn't matter, but the easier ones to use are going to be the 2 and the 3, and I can find A or B by using those using those particular numbers, and they're easier because they're whole numbers. So if I want to find angle A, well, angle A, 3 would be the opposite, 2 would be the adjacent. So I can say that angle A, the tangent of angle A, is going to be the opposite 3 over the adjacent. Now, how do I solve that for A? Well, I have to take the inverse tangent on both sides, which will then give me the inverse tangent of 3/2 equals A. I switched the sides, by the way, on the on that equation. So if you were to take the inverse tangent, now you plug that into your calculator. It is always going to give you out, in this case, the correct value in between the domain of negative pi halves to pi halves. And since 3/2 is already positive, it'll spit out the acute first quadrant angle that tangent would be equivalent to. So angle A, by plugging that into the calculator, will be approximately 56.3 degrees. And then I can do the same thing for finding angle B. Just know that this time the opposite and the adjacent are different. They switch. Because if I'm looking at B, the opposite is now 2. So the tangent of B is 2 over 3. So taking the inverse tangent of both sides will give me B equals the inverse tangent of 2/3, which has an approximate value of 33.7. Of course, we didn't necessarily have to do it that way, considering that we had, let's go with red, considering that we had that, and we already knew that we had a 90-degree angle, we could have just subtracted the difference from 180, adding 90 and 56.3 together to get that 33.7 degrees but either way works. All right, so let's do an actual practical example of this. And this will pretty much be the only example that we do. There are lots of examples and things you can use for this, but again, should be somewhat of a review. Um, there's a bunch in your book actually that have to do with bearing, which is actually a really cool thing. I'm just not going to be testing you on it. Bearing has a little bit different thought process involved there. However, if you plan on going into the Navy, you probably want to learn something about the bearing stuff. So let's just say that we've got some kind of a mountain. Maybe it's at a ski lodge or something. I don't know. So here's our mountain. This is really, really horrible drawing, but there's our mountain. And down here is the base of the trail that you'd be skiing down or whatever. I don't know. Who knows? Or maybe it's the ski lift going up. Doesn't really matter. So we've got this ski lift or whatever going to the top of the mountain. We know there's a specific distance over here to the center of the mountain, and we know that there's a specific height associated with the mountain. What we're going to be looking for in this particular problem is we're going to be looking for the angle of elevation of this slope or ski lift or whatever it is. It's either coming down or going up the mountain. I don't know. Haven't really decided. But in order to know that, what you need to know is we need to know what a couple of these distances are. I either need to know that horizontal distance to the center of the mountain, or I need to know the vertical distance of the mountain, or I need to know the distance of the, again, the ski slope or the ski lift or whatever we want to call that. So in this case, what we're going to be told is that this piece right here is 14,100 feet. So the length of that ski lift or the length of that slope, if you're coming down or whatever it is, that's 14,100 feet. And we are also told that the height of this mountain, this piece right here, is 3,100 feet. Given those two pieces of information, now I can actually find the angle of elevation. Now, in all honesty, the real application of this is probably actually to find the height of the mountain, to be honest with you. If you can set up something where you can point, your camera at a certain angle to the top of the mountain, and you know the distance that you are away from the top of the mountain, either horizontally or on the slant, then you could actually figure out the height of the mountain. It's probably how they did, finding the heights of Mount Everest and all those other things, because obviously there's no way you can take a ruler or a string to the top of the mountain of Mount Everest and go straight down into the earth and figure out its actual height. So they used all trigonometry to do that kind of stuff. In any case, if I wanted to do this, I know the opposite in the hypotenuse, which would be sine. So we would take the sine of whatever b is and get the opposite, 3,100, over the hypotenuse, 14,100. And in order to find the angle, we would take the inverse sine of both sides. So then that would give us b equals the inverse sine of 3,100 over 14,100. And the approximate angle here of elevation would be about 12.7 degrees. And I know absolutely nothing about skiing, so I don't know whether that is a steep or not slope or ski lift or, again, whatever. Anyway, so you could use this kind of thing to find the height of a building. You could use it to find distance, from something on the ground to something in the air. There's all kinds of applications, and they're really good applications for this. But that is, I think, all we're going to do for this video, because I think this is pretty much just a review. We'll do much more with application-based stuff when we talk about 5.2 law of sines and 5.3 law of cosines. All right.